Hi, my name is Kwan, and this is my presentation for clock generation with a focus in implementation of phase lock loop. Okay. So the agenda of my presentation will include an introduction, some fundamentals of phase lock loop, discuss about digital phase lock loop and all digital phase lock loop, some conclusion, and finally the list of references that I used for this literature survey. Okay, so for the introduction, as all know, clock is very important, and since 1600s, there's a need for synchronization between clocks and some sort of reference signal. And in early 1900s, some innovative electromechanical devices were invented to synchronize the pendulum clocks like this with a reference clock, which is back then the clock is usually referenced like this. This is where the clock signal in Europe is generated. It's the Greenwich Observatory, and from here the telegram poles is sent to other places to synchronize clocks. And later in 1930s, the first electronic phase lock loop were innovated based on these previously built electromechanical devices to synchronizing clocks. And since then, the phase lock loop has been modified a lot, and new designs have been invented, like from the conventional analog phase lock loop. There was a digital phase lock loop and all digital phase lock loop. All of them will be further discussed in this presentation. So let's talk about the fundamentals of phase lock loop. So the idea of phase lock loop basically just to output a signal, a clock signal that is that has a frequency and phase or phase aligned with the reference input signal. Like right here, we can see that the output signal is aligned in both phase and frequency with the reference one, while in here only the frequency are aligned. This is like the black box definition of phase lock loop. And for the application of phase lock loop, there have been a lot of applications, but the four most significant ones are standardizing frequency, which generate a frequency that is a multiple, generate a clock signal at a frequency that is a multiple of the reference signal, as you can see in here. And it also the application and the goal that I want to primarily focus on in this presentation. Other applications like tracking complex variations and clock signal, synchronizing across chips, and especially in 3D chips, is become more important. Time recovery, also other applications. And the structure of a phase lock loop is basically that has like three basic blocks to synchronize on the output clock with the reference input clock. So it has a phase detector. Usually phase detector, it can also feature some frequency detector as well, some loop filter, and finally a voltage control oscillator, or VCO in short. And the VCO here, the output is a output signal which is aligned with the input signal here. It also feedback. The feedback of VCO also push back to the phase detector, and these two are actually the two that are aligned to each other. Next, we can go with the conventional design phase lock loop, which is the analog phase lock loop. And it also called linear phase lock loop because in this design, mostly the relationship between input and output are quite in terms of linearity. So let's say the phase detector. It calculates the difference between the phase difference between the reference and the feedback here, and the output of phase detector is linearly proportional to that difference. Similar with the VCO here, the output signal is proportional to the input signal here. And also the structure remains quite the same, with phase detector, low pass filter for the loop filter, and finally the VCO. And in here for synthesizing clock signal at higher frequency, the counter, the frequency divider is added. And how adding a divider can actually multiply the frequency. So as you can see here, the two signals that are aligned with each other, the reference signal here with the FREF and the feedback signal here with let's say the frequency is F feedback. The frequency of these two and the phase of these two are aligned by these three blocks, and it will output the output signal so that the feedback signal is aligned with the reference, which means as soon as the difference between the phase difference and frequency difference between feedback signal and reference signal is locked as in the circuit in the graph right here, it reaches 0, then FREF is equal to F feedback. And because this one is the frequency divider, this one will be the clock signal with the frequency that n times larger than the input signal, and that's how the phase clock loop generate a new clock signal at a much higher frequency. And it is very important. This is a very important application of phase clock loop, as it can use as input clock signal at a low frequency to minimize the power consumption of the oscillator, but then it can create a clock signal at much higher frequency according to the need of the circuit. Another another modification of phase clock loop is the charge pump. So basically, the phase detector, it outputs two signals up and down, and these two signals will control a thing called charge pump. It will inject more current into filter if up is on. Otherwise, the down is on, and if the down is on, it will drain the current out of the loop filter. This block will have added accuracy and reducing noise of the output signal. Next thing I want to tell is phase detector. As we discussed how it takes in two inputs, the reference signal R and the feedback signal V. Then how does it calculate the output signal that represent the difference in phase and frequency of R and V? So mathematically, it first computes the phase difference between R and V, which returns the theta E right here. And the output signal UDT will be proportional to theta E by multiplying with the KD, which is the gain of the phase detector. So that's a mathematical side. Then how it is implemented. So there are two main implementations. One is using the exclusive OR logic gate, or another one is using analog multiplier. In here I have the exclusive OR logic gate. So let's say F1 and F2 input in here. These two signals are then compared, and every time they are opposite in the sign, the output will be 1. And because this the time between the time that one signal is opposite to the other in the sign is also equivalent to, it is proportional to the phase difference between those two, and we can use it to generate a signal, that a square signal with a duty cycle proportional to the phase difference. And using that square wave, we can put it in low pass filter, and the output of the low pass filter will be a signal with the effective DC voltage proportional to the difference in phase between F1 and F2. That is how a phase detector can output a signal proportional to the phase difference. However, in here we actually assume that F1 and F2 are in the same frequency, but in real life it's not that ideal. Therefore, we need to use something called phase and frequency detector. So we also have to account for the frequency difference as well. Like in here, we can use the dual loop structure by adding a whole new loop for frequency difference. But then it will introduce some sort of extra hardware that we need to that will cost a lot, and it also introduce some noise to the VCO. So there's come a new design using these two different to detect the phase and frequency detector. As you can see in here, you can detect the phase difference in these two graphs, and for frequency difference, it can be detected using these two graphs. It can detect both phase and frequency difference. The next block is the loop filter. So basically, the loop filter in PLL are mostly low pass filter. Widely uses first order and second order low pass filter because they are both inactive component passive filter, and it costs less power or area than an active filter. In the second order filter, also lower the voltage noise of the output signal, which is a very good addition to the filter. As you can see here, I have a first order low pass filter, and here's a graph of the output voltage in terms of the frequency. So the next thing is the voltage control oscillator, or VCO. It's as I say, it produces a linear output of the so the output signal is linearly proportional to the input voltage right here, as you can see. And usually the VCO will be broken into two blocks for easier of control the oscillator using the current, and so that we have to use the voltage to current or converter. And in general, the analog PL has done a great job in the electronic field, but as the CMOS technology progresses into the sub-nanoscale, with the trend to lower supply voltage, to lower the power consumption and lower output impedance, it poses a threat into the current leakage in capacitor. And this has been proven by an experiment using a 90 nano CMOS technology and running 1 GHz. The deterministic jitter can reach up to 40 picoseconds. And this jitter can be eliminated, but it will cause a lot of area using the MIN capacitor, so it would take like 20 times more area. Okay, and the next would be the next design modification would be digital PLL. So we all know there are some drawback that analog PLL has. So what if we can digitize it? So some basic idea of digitizing the phase lock loop is we find which one of the reference or the feedback signal to the phase detector is faster. It will detect it will define the output function E of S, and this E of S basically will put into the charge pump as a switch, as a control signal to the switch, and it's like a one bit signal to control the VCO. However, this one will be a basic implementation of how we can use a phase and frequency detector, like we discussed before, in combination with a charge pump to digitize the signal. So in here, it would either be 1 or 0. And there's a waveform of up and down to control. However, there's another modification that is quite impressive, that I find very impressive. So it can using the mathematical side of the transformation of the input to output signal of the analog PLL. This paper has obtained an S to Z transformation. So we have Z here, and using a mathematical, we can work on two gain, which is a proportional gain and the integral gain here to tune the loop filter. The DCO stay the same, quite the same. The DCO stay quite the same with the DCO as analog, and the divider stays the same. But the digital loop filter has been digitized, and also the TDC, which is the new block, is the time to digital converter, which will be discussed right after this. So the TDC, it performs quite similar to the phase detector, as it detects the phase difference between the two signals. However, it's quite different in the output. So instead of outputting an analog signal, it generates a digital word based on the difference in phase and frequency of the input signal. So the basic implementation would be using a DFF, a D-flip-flop, with two inputs as the reference and the output, the feedback signal right here. So if the reference input is faster than the feedback signal, then the output bit, or the V of TDC here, it will be high. Otherwise, it will be low. And using this one bit, we can control the DCO to tune the feedback signal to align with the reference signal. However, there's another stochastic TDC that I found quite impressive. And this one, it will generate a probability of which one is faster. And so let me introduce these circles here. They represent additional voltage, an offset voltage, that the value of that offset is normally distributed like the graph here with the mean of 0. So it means some of them are accelerated. Oh, actually, the offset voltage is designed such that applying this voltage will create a proportional delay in the signal. So let's say you have all of the reference signal input to one offset here, and then they are input into the alternator between the reference and the feedback signal here. So let's say because the offset are normally distributed, if we have R and V are aligned, then they are 50% that some of the offset will make the reference faster, and 50% will make the reference slower. And all of those signal here, let's say if reference signal is faster, this one will be 1, otherwise it will be 0. All of them will be wired to this adder, and let's say we have n lines and the parallel lines here. Then if the difference is 0, then the adder value will be n, half of n. Otherwise it will be somewhere in this line. Like if the the value of the adder here is too high, which means the delay is back here, and it will returns a value that is related to the difference in phase, but it is not linear, because it's not a linear relationship, because this is normal distribution. So it will establish a nonlinear relationship between phase difference and the output digital work. And to compare the digital phase-lock loop with the analog phase-lock loop, we can see that these two graphs of the waveform of how long it will take the analog phase-lock loop up here to get into the lock stage, which is the difference is 0 here, and down here is a digital phase-lock loop, and it will take much shorter amount of time to enter the lock stage, as you can see. And it also this graph also shows that the time it needs to lock in to enter the lock stage for the digital phase-lock loop is much lower than the analog phase-lock loop. It will also require stable across increasing frequency, while the analog phase-lock loop will take more times as the frequency increases. So that's one big advantage over analog phase-lock loop. And then we have something called all digital phase-lock loop. As we remember, the digital phase-lock loop only transform the phase detector into digital, and also the except for the filter and the VCO, they are all remain the same. So in here we have all digital phase-lock loop, which is like a proposed architecture for the digital phase-lock loop, and all of them here will be digital. So as you can see in this architecture, it has like two separated DCO, which is a digitally controlled oscillator. Why, you may ask? So one of them, the tracking DCO, is used for feedbacking the signal, the output signal, to the phase and frequency detector here to align with the reference clock. But the average DCO here is used to averaging the output clock, which means after every iteration of running in here, this one will have to find a sense of what should be the average voltage and frequency for the output signal, and that would use the average mechanism discussed in the paper. In the output, using that mechanism, the output signal will experience much less noise and jitter. And there, when designing this system, the author said there are two key components that need to be paid much attention to. First of all, there are these two DCOs. They need to be at high resolution and a wide range so that they can have better accuracy and also to capture the voltage, the required voltage, much easier. Introduce and alongside that, the PFD, the phase frequency detector, also needs to be designed so that it has as small as the smallest dead zone as possible. So the DCO is designed here with so here's the design for the DCO to have a high resolution and a wide range. So actually the DCO will be divided into three separated stages. First of all, there's a coarse tuning stage, including these array up here. That's array up here. So there are 16 in this design. There are 16 different delay path groups. They are named from Z0 to G15. And each of them will have, each group here will have 8 different delay paths. And for example, between each path group, they will have an inverter to increase the delay to the signal. So, according to the controller previously shown here, the all digital PLL controller, they will use the DCO code to an average code for the average DCO. This will perfectly tracking DCO. That code will be used in here to select the delay path within each group. So there are 16 groups here. The first tuning stage will take one delay path from each group using the con signal in here. The con signal is here, and then all of them are proven to the F1A signal in here, and the closer design will be this one. And from those 16 delay paths, only one of them will be chosen to be perceived as a clock signal. And to select that, we use the F1 on code in here, 32 bits to select that. And finally, the second fine-tuning stage, just improving the resolution of the output signal using the of using the F2 on code right here. And the other one that also been implemented is a PFD, the phase frequency detector right here. So it's quite similar to the flip-flop architecture, but in here, after outputting the up and down signal, they also added some signal extender and other pulse amplifiers here to minimize the dead zone of the PFD. And then they also return back to they're also here to control like the 2D flip-flop, which puts the lag and lead flags right here. And that's my design. That's my presentation for phase lock loop. With some conclusion, as you can see. If we compare analog and digital phase lock loop, both of them still have some analog components, and those analog components will be much inefficient to scale as the CMOS technology into the sub-nanoscale, and it also poses a great threat for noise as a low voltage supply and also high jitter. So that's some disadvantage of analog and digital PLL, and therefore we have come up with the researchers have come up with the all digital PLL, which because it's all digital, it's not limited or require a minimum voltage supply to be accurate or operational. That's why it is fully synthesizable and easy to be scaled as a CMOS technology will reduce the dimension. And it also feature a wide voltage range and frequency range to be captured and to be synthesized. And the output signal will experience much lower jitter, and the whole block will consume less power. And therefore, as we can see, ADPLO, all digital phase lock loop, have shown that they have better performance but at a lower cost. And that's why the ADPLO has become more popular than the conventional analog and digital phase lock loop. That's my presentation. Thank you for listening. Here are the list of my references. There are 3 conference papers, journal papers, and also reference from these 2 textbooks. Thank you for listening.